say, stars. That'll be very interesting to the people that study the stars. But to put that in coordination to our solar system or the galaxy at large that those stars are part of is our job.
So now you get the whole sweep of the universe.
That's right.
So land is the whole freaking universe.
So also, I should say that the program last night, after bringing us back down in light, essentially from the most ancient light we can see, which is the cosmic microwave background.
In microwaves, yes.
Because as we look farther out, we're looking farther back into the past. That as we come down, we then hand it over to Joy Hirsch, who's the director of the Columbia Brain Lab, and she talked about really the difference between photons and essentially the light in our mind in a sense of understanding. And so we're really trying to address this issue of the universe around us and the universe that we know in our brains.
So you went from the outer universe to the universe of our inner mind.
Correct.
Good.
You know what that reminds me of? When I was in college, I took a lot of drawing. I was like a art minor, and I remember one of our teachers telling us to squint our eyes, because what we thought we were seeing and what we were seeing were different things. And he said, if you squint your eyes and you just draw the shadows and draw, the shadows and the light, and then it was so weird because you look up and all of a sudden you have a whole image,
mm-hmm.
and it's what you were really seeing.
Yeah. So Brian, how do we know? I mean, how do you distinguish? I mean, both of you, Brian and Carter. So there's what is, and there's what our perception is. And how do you make the two work to get the most effective show?
Well, when we look up and we see stars, we can sort of have a sense that they're different distances. But to really see the layout and the distances, or say where the planets fall in this, because look up in the night sky tonight and you'll see one of those bright stars, so to speak, is Saturn.
It's Saturn
and
in the evening sky. It's a beautiful sight tonight.
And we were showing that with the World Science Festival just on Friday night, which was wonderful. And people always
right under the Brooklyn
through.
Bridge. That
yes,
was a beautiful setting.
Yeah,
if people don't know, this time of year, every year in New York City, there's the World Science Festival, and some of the greatest scientists in the nation and in the world descend on New York and bring science to the public in many different venues, one of which was the Hayden Planetarium last night.
But if you look at the grand tradition of natural history museums, you typically have a diorama. So you'll have taxidermied animals, and then you'll have the grass or a tree, and then you have a backdrop painting, which is too far to really discern some depth to. So in a sense, we have a digital diorama of the entire universe. A cosmic
diorama of the universe itself.
But it's accurate. It's an authentic experience.
And when you can walk through or journey through while not even leaving the seat that you're in.
And the data authenticity is Brian's job.
When we come back, more from Let There Be Light on StarTalk Radio.
Unlocking the secrets of your world and everything orbiting around it. This is StarTalk.
This is StarTalk Radio. I'm your host, Neil deGrasse Tyson, astrophysicist with the American Museum of Natural History. You can follow us on Twitter. StarTalk Radio is our handle. We're also online, startalkradio.net. And, of course, you can like us, StarTalk Radio on Facebook.
That sounds needy.
I like you, Neil.
Brian Abbott, manager of the Digital Universe. You had some comment just before the break about the difference between how a scientist views data and how you guys make it alive.
Yeah, what struck me when I started working on this project is that scientists see their data not only as a 2D graph, but also they only see their data. They don't see it in the bigger picture, the bigger context of where that fits in the universe.
So the visually
2D isn't two-dimensional, right?
Yeah, of course. Yeah,
okay.
yeah.
This is 2D.
Okay. So they have a
Sorry,
narrow
it's not 2D, 2D fruity. 2D, yes, 2
2D.
dimensions, yes. So it's a really boring way to look at the data, and you might miss the bigger picture.
Yes.
And so, Carter, you make the big picture is what you do.
Right. The scientists understand the bigger picture, and that's their job. And it's our job to, again, create that continuous experience from Earth all the way out.
One of the most moving moments in this journey is when we pass by the radio bubble. Tell us real quick about that.
So, yeah, if you actually look out into the stars, you can say, okay, they're different distances. But if you stand away from the Earth, let's stand away from the Earth about 100 light years, you would look back and you'd see a sphere. about 70 light years in radius.
That's if you had radio-sensitive eyes, you'd see a sphere.
No, you'd have to actually be detecting it and be at the sphere.
At the sphere, okay.
But what we do is we draw a graphic of a sphere, and that indicates how far radio signals have traveled since the Earth became radio bright. You had Tesla and Marconi and early radio that bounced around inside the ionosphere.
So it's not when Earth became radio bright, it's when human beings on Earth became radio emitters. Right?
Yeah, that's right.
With their apparatus.
With radars and television carrier waves. And so you can see that moving out. So if you parked next to Arcturus tonight, which is up in our sky, you would
let's plan to do that. Yeah,
you would be hearing radio broadcasts or TV from 40 years ago.
Yeah, see, I have that question. If there's all this stuff that we can't see, all these waves and light waves and things
penetrating your body right now,
then don't they all bump into each other? When is there too much, and what happens?
Yeah, no. The interesting thing about is they can interfere, but they only interfere if they're sort of coherent. So a laser, you can make lasers interfere, and you get like what's called fringe patterns.
Oh, before we leave, I have to know: are there lightsabers?
Oh, you mean like in Star Wars?
Yeah.
No. Okay. So now.
So, he told me to wait and ask on the air.
No. Here's the thing. No, you can make a beam of light that would be visible, such as lightsabers.
Like your light beam thing that you use to point.
And I even tweeted this a few weeks ago. Lightsabers would not hit each other; they would just pass right through one another, and you wouldn't have these sword fights the way they would show it. They would just pass through one another.
What kind of light is lasers made out of? Like
it's visible light. You can make other kinds of laser light, but the ones we're most familiar with are visible.
The radiosphere sort of sets us up in a sense that if you go away from the Earth far enough, you're going far enough back in time. Everything we see, a star twice the distance away is twice as far in the past, essentially. So if you look far enough, you're actually seeing the cooling off of the universe, or the transition between when it was a plasma and opaque to where it became clear space. And that's the microwave background that we see.
So you not only show us
the
radio bubble that we created, that's now about 100 light years out,
right.
And all of our civilization, as we've communicated it through each other,
that's
has leaked into space and is contained within this bubble.
So you show like if God were to look at it.
Yeah, but those
or Carter, yes.
those are waves moving out, our radiosphere.
Mm-hmm.
But the stuff that's coming to us is essentially, you can imagine a sphere, very large, that's a microwave background, and everything that we can observe is contained within it. And it's centered on us, but that's just because it's us observing it. If you moved anywhere else, you'd also see a sphere around you.
It would feel like you're in the center of that. So now we're in.
Carter creates like accurate art.
Yes, and that is the hallmark of the 21st century.
Pictures from data.
So, that's like he gave the analogy a moment ago with the dioramas, something that the American Museum of Natural History pioneered 100 years ago, where you create. It's not just an animal stuffed on a pedestal. You put it in an environment that transports you to that local to that location.
Cool.
Yeah. So now we're in an expanding universe, and this microwave light and all the light in the universe is getting diluted in space, and its energy is dropping, and so the universe, I don't know if you knew this, is approaching. The universe will not end in fire; it will end in ice, not with a bang, but with a whimper. And
I saw that movie.
Yeah, well, it's a poem. It's a T.S. Eliot poem
heat
as
death.
well. So they call it a heat death, but it's really a cold death.
How do you equate that with global warming, Neil?
Yeah, so
I don't know. Does that mean that you don't believe in global warming?
Earth
Neil?
is insignificantly small compared to the scale of the universe on which I'm referring. And so the temperature of the universe, of this cosmic microwave background, you can actually stick a thermometer in it and get a reading. It's about 3 degrees absolute temperature. 3 degrees above absolute zero. So, and we're about 14 billion years old. When we're 28 billion years old, we'll be 1.5 degrees. And it'll scale right on down until we asymptotically approach zero. And the day will come.
Really?
Well, as you approach it without ever actually hitting it. You get closer and closer without touching
everyone just looked at you like they knew what you were talking about. I'm like, asymptotic.
Asymptotic. You learn that in Algebra 2 and trigonometry.
Oh, okay.
In high school. Yeah. So
skipped it.
So all I'm saying is that the temperature of the universe will continue to thin out and get cooler and cooler and cooler. Stars.
Is that bad?
Well, yeah, I think so. Yeah. Stars will eventually run out of their fuel. They will die. Even the clouds, they'll make whatever stars they can, and then they'll die out, and then all matter will be left will be left in the remnants, the dead, cold remnants of stars that once were.
The universe sounds feminine. It sounds like women. Like you have to work really hard, and then the Earth is just men.
Well, once these
around.
energy sources run out, the stars will turn off one by one, the galaxies will shut off, and the universe will turn dark for the remainder of eternity. Brian, how can you say anything after what I just said?
Downer.
Well, it's fascinating that future astrophysicists will not know anything about cosmology because they will not see any of the galaxies out past our local group.
Oh, because we will expand so fast that our galaxies will expand beyond the horizon.
But that's not true, because if you look far enough away, you will see some of that radiation coming toward you.
By
By
that's
then,
another show.
By then, we're going to have faster than light travel, and we'll have sources. We'll be able to make our own stars, and we'll be able to zap.
And Michael
around
Benson's been reading tons of science fiction lately.
Of course,
Yes.
I mean, come on, let's not be so grim. We'll fix it with technology.
If you look far enough back, you can see the heyday of the universe.
Would that be the end of all light? I'm
It
freaked
would,
out.
in fact, be the end of all light and the end of all physical processes there ever was.
This is a bummer. Can we leave on a good note?
Sure, I've got my tweet of the week, the StarTalk tweet of the week. Let's see if I can leave you on a poetically beautiful note. May I?
Please. But thank you, guys. You are all awesome.
Astrophysicists do not fear the dark because telescopes reveal the night to be ablaze with bands of light our eyes cannot see. This has been StarTalk Radio. Thanks my guests, Carter, Brian, Lynn, Michael. We're partially funded by the National Science Foundation. I'm Neil deGrasse Tyson. Lighten up for
Lighten up!
StarTalk Radio. We'll see you next time.